Ты можешь отсюда уйти, вам везде. Прям можешь встать и уйти. А ты помнишь, кто название придумал? Кто название придумал? Там функция Krichever. Ну как, это же наша с тобой работа. И мы тогда решили все называть своими именами. Я сейчас просто хотел про это сказать.
Okay, welcome to our last morning session talk, and I'm happy to introduce Andrei Marshakov who will speak about Krichever tau-functions old and
Thanks to the organizers and to the participants of the school. And well, it is a great pleasure to speak here, and especially on this special day devoted to the memory of a great scientist and my very old close friend for more than 30 years. We knew each other, who taught me a lot. And one of the ideas, well, why I decided to speak about this subject, about Krichever tau function, which is a very nice object, very simple object. In a sense, it's the most simple geometric example of integrability, which is maybe not known and not well known in modern scientific language to young people. Sometimes instead of formulas, which were actually originally derived by Igor, they use some strange words like, topological recursion or something like that, which is just an extension of this, but corrections to the main contribution given by this Krichever quasiclassical tau function. And so I will try to give you some basic definitions to be maybe first in spirit of lectures given here, and then try nevertheless to say something about modern developments, since as any interesting scientific contribution, it has some natural extensions, and this object has many natural extensions. Maybe I will try to concentrate about, well, some sort of a puzzle discovered recently. And so anyhow, let's start with this old story. And so it comes from this paper by Igor Krichever, which appeared in Archive in 92 and then was published in 94. And this is quite in spirit of this small movie we just saw today, and particularly Nikita's comments. These are very close to my own reminiscence, the days of old ITEF, which no longer exists, and how the science at that time was developed. And in particular, it was mostly appeared around this subject, so matrix models of two-dimensional gravity and topological strings, just exactly as you heard already today. And actually what Igor did, he defined all this scientifically. So that was a puzzle for me, though I was not as young as Nikita those days as well as now. But indeed, it was for me quite a puzzle that the objects we were deriving when studying this sort of physical applications, that they can be defined in purely geometric way. And I recommend very much to read this paper, where a lot of ideas are even hidden, and so I was the whole my life coming to it back and back. And well, try maybe to describe the main issues. There are 2 points immediately to be pointed out. So this is just original title with the word tau function in it. Though the letter tau, if appears in the text of the paper, is neither in that sense. Because actually, so since this is the story about semi-classical contribution, actually one has always there the letter f, which is the logarithm of this tau function. And everything is defined through this f. And second is maybe that the weakest point of this paper is terminology. This overcomplicated notion of tau function of universal Witten hierarchy. And I believe that probably from first from our paper with Nekrasov of something like 2007 or 8, the right notion of Krichever tau function should be fixed in the literature. And so then I will try to just give you a hint, so how it is defined, and discuss a few examples. One of the most famous examples was its further application to Seiberg-Witten theory, its reformulation in terms of integrable systems. And then I will come to one of the maybe most nice and essential formulas from this Krichever approach, is this residue formula for the third derivatives of this tau function, for the logarithm of tau function. So sorry, I would often omit this log. And maybe some, again, historical, very simple context, how it can be, say, applied to make a very simple statement about WDV equations. And so then this new story, so it contains many possible developments. So I just listed here 2 of them. And maybe if I have time, I will try to say a few words about this quasi-periodicity in science, if you wish. So the science started with 2-dimensional gravity, and then many people claim that everything was solved there. But now it's on a different level, on the level of some exact comparison with the worldsheet calculations. And then, when you try to think about that, some new puzzles arise in this context. Okay, so let's try to say something so simple, just notations. So first of all, we deal with compact oriented Riemann surfaces or complex curves when the only topological characteristics is genus. And then, so the dimension of first homology is 2G. And so it means that you can choose 2G independent contours and use some symplectic intersection form, so that commonly known as the set of A and B cycles. So with intersection A with B to a delta function and minus in the opposite direction. So the dual basis, so to say, is given, can be given in terms of first kind holomorphic abelian differentials. And so is usually, so Igor always corrected me, the right word for them is normalized, if they are normalized to A cycles, so that this matrix is just a unity matrix. And then the other set of periods gives the period matrix of Riemann surface, which depends on the complex structure. And so the first and very old point is the set of Riemann bilinear relations or Riemann bilinear identities. And maybe the most known is that one which gives to the fact of symmetricity of the period matrix. And actually this fact is the core point of integrability here. So the line of argument is very simple. You just take a zero, which is an integral of a holomorphic to form over one-dimensional complex manifold, and then you cut your Riemann surface in for G gone, and use the Stokes formula. And using the Stokes formula, just looking carefully at what is written here, where this omega b is the abelian integral of a holomorphic differential, which is well defined on a cut surface with differences on two different copies of a cycle given by corresponding period. You just carefully look at the Stokes formula and get this form of relation. And if you remember the definition of normalized differentials, this is just an antisymmetrizer of the period matrix. So it's obviously zero, so the period matrix is symmetric, and this is the first example. Then, well, very similar identities can be written for other abelian differentials, and as usual in the theory of integrable systems, well used two other sets of abelian differentials. The second kind, which have some higher order pole singularity at a given point, and commonly so it is chosen in the way that the local coordinate is adjusted in such a way that only the highest possible term survives here. And since any such meromorphic differential can be defined up to adding a linear combination of holomorphic differentials, so it can be fixed by imposing certain conditions to its periods. For example, again, common normalization is the A periods are all equal to zero. There is also another third kind of bipole differential with two singularities of first order. It can be written in terms of a prime form on the Riemann surface, and it has such sort of expansion. And again, it can be fixed by imposing the set of vanishing of all its A periods, which is in agreement with such formula. And if you apply the same logic to the, say, holomorphic and this bipole differential, you get another form of Riemann bilinear relation, so relating the B period of meromorphic differential with the integral between singularities of a holomorphic differential. By the same logic, you again use the Stokes formula, but now only take into account that there are other contributions. Since this differential has singularities, there is a contribution from its two residues on the cut Riemann surfaces, and so which actually give rise to this term. So, any questions? I hope that everyone knows that. Well, if not, then you should just check. It's very simple. Maybe the most evident is if you do this on torus and obtain some known identities for the periods of quasi-periods of elliptic functions. Yes, you definitely know, yeah. Why? Any such two contours, yeah, that's probably there is some, yes, delicate point, but probably you're right, yeah. Even actually I forgot how it is fixed. Because maybe it's related with these logarithmic singularities of that. So it's somehow related to the choice of the branch of logarithm, right? So all other students should take this example for student Professor Nekrasov to ask questions. Very nice. So now to define Krichever tau function. So first of all, again, some extra thing is what again I think should be called Krichever data. It's what Igor liked a lot, a curve with a pair of meromorphic differentials, let's call them dx and dy, with the fixed periods. Well, the fixed periods means that they are either, say, a very typical example is a family of hyperelliptic curve when you have hyperelliptic coordinates and all periods are zero. There are other things like this sort of bipole differential when its periods, because it's d of logarithm, they are all integer valued. Basically, it means that they do not depend on moduli of complex structure of your curve, but sometimes it's even more. For example, if your curve covers a torus, like in the case of Calogero model you consider in these lectures, so sometimes this tau, the modulus of a torus, is also considered to be fixed, and you vary only the moduli of the cover. So that's not a very strict, but intuitively very clear definition. And the point is that if you fix the periods of these two differentials, meromorphic differentials, so roughly you impose 2G conditions. It's not, I understand that I cannot honestly count all these small numbers like this 3. It's not exactly 2G with some modification, but basically in the limit of large genus, you extract 2G from 3G and get G at the end. And this is so you for the curves with Krichever data. So you get a G parametric family of such curves, and basically it means that you get an integrable system. So you consider a G parametric family where the role of these G parameters on moduli space is the values of Hamiltonians of your integrable system, so the action variables or action variables, while the coordinates on Jacobian play the role of complexified angles from the Liouville theorem. And so this is the right context to introduce this function. And so let's come to the definition. I start from one particular case, which is, now well known by the word prepotential, because it had some particular application in the theory of supersymmetric gauge theories, though, as I just tried historically, it was introduced by Igor several years before. So, starting point is this Krichever data, G-parametric family of Riemann surfaces with two differential, or I can formulate it differently. I can say that they form these dx and dy y generating differential, and you have a connection on moduli space such that the derivative of this generating differential with respect to this connection is holomorphic. So I will try to illustrate this words by some particular example. Basically, this connection is defined by its covariantly constant section. So by a function on two different curves in curves which are correspond to different points in moduli space, but which you consider this function you consider to be the same. So the problem is that you actually have this moduli space M, and you have to compare something on the curves above two different points in this moduli space. So that's the point. And then once you have this, you can define a prepotential, a particular case of this Krichever tau function by the following set of formulas. One set of the periods of this generating differential is considered to be flat variables which respect linear structure, while the second set of the periods give the gradients of the quasi-classical tau function. So that is, of course, a very non-trivial statement, since you have several quantities, generally except for a torus, which are expressed in terms of derivatives of a single function. So what is the condition? Condition is integrability, and it follows directly from Riemann bilinear identities. Since if you take the cross derivatives of dual periods, so-called, over the flat variables, you get a period matrix, And this period matrix is symmetric, which is ensured by all this data listed here. Since it is symmetric, so these gradients indeed can be integrated up to a function. So clear? So now, so what is the proof? So the proof is more or less obvious, as I said. So once you have this condition, you take covariantly constant function, for example, this x, and except for the points where there can be some problems, and we'll discuss them at the points where this differential turns to 0, because there x is not a good coordinate. You just don't have such formula, and if what stays here is holomorphic differential, then there are just two exercises on derivative. First, you take this derivative where the derivative is taken implying the existence of such connection. Then this is an integral of a holomorphic differential, so which is a delta function, which means that this is a normalized holomorphic differential. Then you take this second set of derivatives. Again, it's a B period of a holomorphic differential, so that's a period matrix. That's why it is symmetric, and everything can be integrated. And as a consequence, we get a simple formula, which is common case for the Krichever tau function for the second derivatives. That's simply that the set of second derivatives of prepotential with respect to these particular chosen variables. So this is not covariant derivative. It respects only linear changes, is given by the period matrix. Questions? Okay. And now this is the mostly, again, well-known example, which is called the prepotential of a pure gauge theory in the context of Seiberg and Witten, where the equation of for the G-parametric subfamily of the curves is given in that form. For those who are interested in integrable systems, one can here immediately recognize a spectral curve of a fine Toda theory with n particles. And so here it's just a polynomial of power n. It has n independent coefficients, where lambda is just a scale parameter. And there are two. So first of all, it's easy to see that this is a hyperelliptic curve, a special hyperelliptic curve of genus n-1. So here are n-1 parameters. It has two differentials with fixed periods. So one of them is just hyperelliptic coordinates with all periods equal to 0. Another one is this d of logarithm with the periods being integer. And the connection can be introduced in a very simple way. As I said, let's W be a covariantly constant function. Then the derivative of z can be found by differentiating this equation of the curve. And we essentially use here that in the derivatives over modular parameters and derivatives over z, you always get this p prime of z. So this is a typical form of these considerations. And so once you apply this formula, you can check that when you differentiate the generating differential, so it's just proportional to this derivative of z, and derivative of z you extract from this formula, and what stands here, again, it's a very nice and simple exercise. Everyone can check that this is a holomorphic differential on this curve. An arbitrary holomorphic differential, so since it's a linear combination of n-1 holomorphic differentials here. You can check that there are no poles in this expression. So say good example why there are no poles at the points where p prime equals to 0. Who can say? Naively, you see that here something stays in the denominator and there should be poles. Why there are no poles? Профессор Вигман. Почему полюсов нет? By what? So Professor Wigman is second good student. Yeah, indeed they are cancelled, of course, by zeros of dw. Yeah. Usually, most of the poles are cancelled by zeros. It's only in Poyer's model, I believe. Okay, so this is a holomorphic differential, thanks to Pasha. Okay, now we can extend this. So that was mostly, how to say, mathematically careful object when you did with non-degenerate Riemann surfaces, but in this original Igor's paper, it was extended, well, for many cases, in particular for this case coming from dispersionless limit of KP theory. And that was, again, historically a long discussion what we should consider in the context of 2D gravity and matrix models. So finally, at the moment, it is clear that this, even in this dispersionless limit, which corresponds from the string theory point of view to contributions of world sheets of only spherical topology, still many things are not clear. So it's enough maybe to restrict yourself to this case to get the truth, and then. But anyhow, so this is the formula from dispersionless KP, where psi here is inverse local coordinate at the point P naught, so that the value is infinity. This is typical for KP theory. And this formula is defined again flat times, so which are the times of the evolution of dispersionless KP, and the first gradients of the logarithm of tau function. The consistency condition of these formulas is again ensured by a simple formula for the second derivative, that this is just a residue of such product. And due to the choice that psi is local coordinate and this d omega n is a differential here of a function where the singular part at the point p naught is given by nth power of this psi. So just due to this fact, so plus means that it's a polynomial in some global coordinate of Ephemeron sphere. This formula is symmetric. And say another, well, of course, you can introduce both such coordinates simultaneously. Then the mixed formula, for example, will be given by B period of second kind abelian differential, which is would be again equal to a certain residue by linear Riemann bilinear identity. And in contrast to the third kind differential, I believe that there is no ambiguity here. Okay, so now, well, to end up with these definitions, so what I wanted to say. So first is this very important issue of, as I said, originally scientific approach of Igor, who defined an object. So many people use this object at that time, but nobody was able to formulate it in such simple geometric manner. That actually this is the object which this quasi-classical integrability just follows from basic property of complex geometry. Second, that it can be defined for any set of abelian differentials, as I said, and in particular here by dots. Well, in the original paper, Krichever also considered some differentials with jumps. And that's also a very nice object, but I don't, to be honest, I don't know examples when they shown up in the applications. Maybe they should be, but if anyone tells me, I will be grateful, but I don't know myself. Then there is this also actually non-trivial issue of this PQ, so-called duality. PQ was some original, again, terminology from two-dimensional gravity. Basically, it's exchange between these two differentials from the Krichever data. And in the non-singular case, for prepotentials, it's almost nothing. You just change the definition of these connections in different way. And sometimes even, I remember, like we argued which choice is better, but basically it changes nothing. But for some cases, it's a very non-trivial issue. Like in the case of DKP, it turns into a kind of Fourier transform relations for matrix integrals. And also it has some non-trivial consequence for the residue formulas, which I maybe come back at the end. And so this Krichever quasi-classical tau function is actually a starting point for this topological recursion, and that I also mentioned and want to repeat again, that sometimes people repeat to these formulas. Just say that these formulas belong to this topological recursion, but to my knowledge, there is no other definition of this main contribution, that actually this topological recursion only describes the corrections to this formula. And from the point of view of physics, it's a bit ridiculous to study corrections, not saying anything about the main contribution staying in the exponent. You see, I don't know what is quantum spectral curve. That's the point. It's a very strange object. Usually, as I understand, people say that the whole topological recursion can be extracted from some certain object which arises if you formally quantize this curve. But it's not well-defined perturbative expansion. And so here all curves are normal classical, moreover algebraic. For Igor it was very important to have some well-defined class of objects, but maybe discuss this afterwards. Okay, now, if everything here is clear, so let's come to the residue formula. It's again an issue. So first of all, there is a statement in the theorem for all such possible choice of flat parameters. There is a unique formula for the third derivatives of this logarithm of this tau function, which is given by a very simple expression. So it's a residues over the zeros of one of the differentials from Krichever's pair staying in the denominator. So the choice of the differential is actually given by the choice of that connection. And that formula is not always symmetric. And here stays the differentials corresponding to this set of times. So that this formula was formulated in the original paper, of course, but the proof there was given only partial for a particular case, though of course Seiberg knew it very well in general, and after some time I managed to extract it from him. So in maximum generality, and so here let me just give an idea. It's indeed very simple, and let's consider the non-degenerate case for simplicity. So how to get the third derivative? You should differentiate once the second derivative. Yeah, there is no other way. Take a period of a period matrix. If we remember that in the prepotential case, the period matrix is a second derivative. Just take one more derivative. Then you have to take a B period of the derivative of this normalized holomorphic differential. Now we use the same trick with a cut Riemann surface and rewrite this single B period in terms of an integral over the boundary of this cut Riemann surface. Looking carefully at this expression, you see that here it's the abelian integral omega b, beta, which actually reduces the whole integral over the cut Riemann surfaces just to a single B period. Is it clear? And further, now you are in a simple situation in some domain in a complex plane. You can just here integrate by part or whatever. So you write this in such a way, and you can then deform the integration contour from this boundary to the interior when it localizes. The statement is that if you have in mind that differentiating with this particular chosen connection, the only set of points when it can be localized is the set of zeros of the differential dx. Just exactly because at these points x is not a good coordinate. How to see this? It's very simple. Just consider the point where dx equals to 0. At this point, for simplicity, I take only these simple zeros. For simplicity, in the vicinity of this point, this abelian integral will have such expansion. So the right coordinate will be square root of x minus xa, where xa is just position of one of such points. Well, now take this derivative. So take a derivative of this expression at constant x. It is clear that it acquires a pole just because you differentiate the square root and it goes to denominator. So this expression has a pole. Now, how can you cancel this? Again, just by taking the differential will acquire such form of expansion. And now, thanks to Pavel Borisovich, we know that this pole here is actually canceled by the 0 of dx. This is exactly an example, as you say. When residue is 0, pole is not cancelled. 1 over z to power 100 has a pole, but residue is 0. If you multiply it by the z, of course. It's not necessarily true, even in Pavel's model. Okay, so now what you see from here, you see that you can apply these two formulas and rewrite this derivative in such a way. So it will be the sum of all points A where dx equals to 0 of this expression, where here stays d omega alpha divided by this square root giving a pole, and this pole can be rewritten in terms of this d omega beta over dx. And the very similar set of manipulations, if you try to do this carefully, you should consider the expansion of a second abelian integral in the vicinity of this point, then dy would be of that form, and taking the derivative of ds would be of that form. So the rest of this formula can be expressed by something divided by dy. So finally, so that what we started with indeed turns into this residue formulas, where in the numerator there are two normalized differentials corresponding to this flat times given by a period of generating differentials, and in the denominator is dx times dy, as I promised you. So please, questions. Well, it may be not so easy to follow all that, but indeed I tried to give you this main idea, and indeed it's a relatively simple exercise. Can we proceed? Okay, now just maybe slightly switch. Now for the most maybe singular case, which is known by the case of so-called Landau-Ginzburg topological theories. I'll take the simplest A series. Here it's clear why it is A series, so it's just given by one polynomial of power n. And the Krichever data is given by this triple, so it's sigma here is a curve of genus 0, so it's just a sphere, which can be parameterized by global coordinate lambda. W is this Landau-Ginzburg polynomial, and the local coordinate is chosen to be w to the power 1 over n. And so this is a particular case of this dispersionless KP theory, actually an reduction of dispersionless KP theory, and you can consider this as a dispersionless limit of the Lux operator. And so I can, for example, recommend a very nice paper of Takasaki and Takebe, where this is described in very clear way. Of course, not only this case, but something more generic. Now, the definition of the set of corresponding differentials or their integrals here, since you're on sphere, you may not even distinguish, is just given by such formula, and it's easy to check that this is just the formula in the right-hand side is exactly the dispersionless limit of KP equation. Plus means the polynomial part of this expression. So generally this psi has this positive, well, when expanding in lambda, it has this negative tail, like the tail in the dispersionless limit of Lax operator in KP theory. So the formula for flat times is given, as I said, by this expression. And, well, just here it can be expressed in such a way, like in particular, it was derived by physicists which did not know at the time the science. And so the derivatives of the Krichever tau function are given by a set of dual residues. Again, they can be described like that. And it's very easy here, just by dividing polynomial by polynomial, to derive a formula for the second derivative, which is this simple expression, obviously symmetric. And this third derivative, similar to what we had in non-degenerate case, is now given by this formula, probably known before as growth and decrease residue. So it's just, instead of two differentials, one of them is just d lambda, another is dw, and so it is concentrate either at infinity, which is non-trivial here, or in the zeros of this w prime. So, while this example may be historically important, because it immediately sheds some light to this context of so-called WDVV equations. Hypothetically, from physics, they are coming from associative algebra of a ring of certain primary fields in some topological string theory. And in Landau-Ginzburg case, this ring is realized as a polynomial ring modulo this W prime. So it's some finite dimensional ring, commutative. And when you just take a product of two polynomials and expand it over the basis of the same polynomials, modulo W prime. The constants of this ring, if you form from them the matrices, they obviously commute. And if you choose a basis corresponding to the Krichever's choice of flat times, these structure constants can be expressed through these third derivatives. And this commutativity relation for the turns into overdetermined system of nonlinear differential equations for the third derivatives, which mostly compact can be written in this form. And this system of equations is known as a WDVV equations. Well, it's of course sort of a puzzle, but these equations can be solved. The solution is given by this quasi-classical tau function. And yes. These hold in many different cases. In particular, say in the cases of topological theories given by quantum cohomologies. Well, in many cases. And there are many other notions. I just consider this is a so-called case of B theory and the simplest case of B theory, where I just given by this expression. And what is important for me now, that in this case, and maybe only in this case, they trivially follow from the residue formula. About other cases, I don't know. Yeah, yes. But here it's absolutely inessential. Then that's one of the points which even... Huh? No, you're absolutely right. Then in the case of topological string, you always have a unity operator, just so-called true vacuum, if you want. And it corresponds to just this matrix given by unity matrix. What was amazing for some stupid people for some time, including myself, of course, and I was not able to realize it before some explanations from Igor, that indeed that sometimes this equation holds without existing this unit operator. And the fact is very simple, that they just follow from the residue formula and nothing else. It's so simple that it's a kind of a shame that we were thinking about this for several years. Yeah, the form is just the same. So what Nikita says is that so originally they can be written, for example, in such way. Where this eta is, first of all, it's matrix F1. The one is this unity operator. And second, in this context, it's always constant. So, and you have here a constant matrix, which sometimes, well, exists, sometimes not. But it makes them simpler. But once you have this form of equation, just by simple matrix conjugation, you can get what is written on the slide under the only condition that all these matrices which you have to invert are non-degenerate. But even if they are degenerate, it's also, there are some known examples, you can just cancel this vanishing determinant from both sides and still equations hold. So it's indeed a little bit subject of overestimated interest, I would say. But the point is now what I wanted to say. So the theorem is very simple. So let f be the Krichever tau function. That simply means that this residue formula holds. Then it satisfies WDV equations once the matching condition is satisfied, that the number of times is equal to the number of critical points in this formula. Taken, what is important, that the number of critical points in counted modulo possible involution. For example, if you have a hyperelliptic curve, sometimes it arises, then naively this differential dx has many zeros. If it is a curve of high genus, then the number of zeros of holomorphic differentials increases. But due to hyperelliptic involution, they can give the same contributions in these residue formulas. And so you only have to check this matching condition. So this is the first remark. Second remark is that upon this non-degeneracy condition, this proof is obvious. And third remark is actually what Nikita said, that originally in this context, it's they arrive with the extra condition that there exists certain metric, actually bilinear form, in the space of fields, which is given by the matrix of the first derivatives, and it is constant. But for this, derivation is not necessary. And the idea of the proof is very simple. You just consider this finite dimensional ring at these points, called here by lambda alpha. So if everything is non-degenerate, so if matching condition is satisfied, then the number of indices k is equal to the number of indices alpha. So this matrix phi k of lambda alpha is square matrix. And if it is non-degenerate, it's invertible, which simply means that you can solve this linear system with respect to these constants. And the same you can do if you just modify this ring by multiplying here by arbitrary xi of lambda alpha, if with only condition that at this point it's not equal to 0. And then, first of all, you define these constants from this linear relation, and you have only to check consistency, say, with the third derivatives of tau function in given flat coordinates. And this consistency says that in the initial case is just given by this relation that this matrix eta is matrix with one fixed index, but generally eta of xi is just simply a linear combination of all of them. And due to linearity, you get back to the equations in such form. So this is a rather trivial statement. The only non-trivial point here, and very non-trivial, is the residue formula. So, questions? Yes, Anton. Number of t is so here or there. So you see, what is this phi I? This is the set of differentials of their integrals corresponding to the flat times. So you just consider a quasi-classical tau function which consists of certain amount of variables. This number is the number of these variables. For example, in Landau-Ginzburg case, this matching condition was proven by Gauss, because it states that the number of roots of the polynomial is equal to its power. What is? No, just this number, nothing else. Okay, so, and now I'll try to make this loop back and return to 2D minimal gravity, from which this story had started. I should be honest because, well, this is still, as I said, a delicate subject. So on general physics background, all people, as I know, believe that two-dimensional quantum gravity is a very simple science. It is sort of renormalizable theory compared to, in contrast to gravity in all other dimensions, maybe except for 3 dimensions. And that is why the result of calculations of some reasonable quantities do not depend on the cutoff on all other details of the quantum theory. And that is why you can compute them in any possible way, as you can. Yeah, for example, you can try to compute them in worldsheet theory, which is a very non-trivial problem. And actually, it was a part of some simple indices. It became possible so open for computations only after the works of Alyosha Zamolodchikov in the beginning of this century and this millennium, though many people, as I said, claimed much more in advance that everything coincides. So this is maybe one of the hardest possible and the most honest way to give the results, but there are other alternative approach. And one of them is usually called matrix model approach, though actually it's not much in this approach from matrix model. So matrix model was more like original motivation for it. But then it was reformulated by Douglas in the form of solution to two-dimensional PQ gravity in terms of KP theory, so that the generating function for the correlators in this gravity is given by Kp tau function for the solution, which is distinguished by such relation for two operators. One of them is Lax operator of, say, p-reduced Kp theory, and another is so-called Orlov-Schulman operator. And and here it stays some parameter, h bar, which is actually a parameter of quasi-classical expansion. So these, as I said, are two differential operators. And in the dispersionless limit, so if you go to sphere, they simply turn in the set of two polynomials instead of operators. The Landau-Ginzburg case formally corresponds to putting one of these integers to unity. And this is the simplest and solvable case. The other are much less trivial. But, well, there are some things still to say about that. So the first one is, of course, these two polynomials. They satisfy equation, an obvious algebraic equation, where if you take the difference of mutually dual powers of these polynomials, then you can compensate this by bilinear combination of lower terms. And generally, this equation defines a smooth curve of genus p minus 1 times q minus 1 over 2, which is a number of primaries and minimal model, which is believed to be coupled with two-dimensional gravity to lead to these results. But in this, of course, particular case, where these are polynomials, this curve becomes degenerate. And here I will even draw you some pictures of these degenerate curves corresponding to this Yang-Lee model 2,5 is this case, and Ising model P, PQ is equal to 3,4. And obviously, this curve has a genus 2, and this curve has a genus 3. Is it obvious? Well, just you can see here two non-trivial, say, A cycles. If you slightly resolve the singularity, and here you see 3 such points. Okay. So now, as I said, if you try to be modest and restrict yourself to the case of contribution of Welch's only of spherical topology, this can be solved to a certain extent in terms of dispersionless Kp. And on rational curve, it just means that this generating differential, again, on rational curve, you can forget about the difference between differentials and functions themselves. It is just a linear combination of this expression, and this is a typical, again, example of Kp theory. And this ds has such expansion, which fits with the definition of flat times and the first derivatives. And all dependencies can be, over these flat times, can be restored from kind of Godot equations, which basically comes in the Krichever approach from the fact that ds equals to 0 at the points where dx equals to 0. If you rewrite it in terms of global coordinate, you get some equations, and in principle, well, these are of course algebraic equations, but in principle they can be solved. Then any Kp Hamiltonian, which is a derivative of this formula, is given, as we well discussed here, literally by kth power plus of this local coordinate. So this is a polynomial, and it is a polynomial of the variable lambda, global coordinate, which corresponds to the first Hamiltonian. So 1 over n plus is just lambda itself. And this fact leads to a set of dispersionless Hirota equations, which say that all second derivatives of quasi-classical tau functions are expressed in terms of the derivatives where one of the indices is fixed to be 1. For example, equation like that. And, well, just to give you a hint how it works, let's say take Ising model, and if you choose, there are two polynomials of power 3 and 4. If you choose this parameterization, you will get that there are 3 live flat times which survive, T1, T2, and T5, and they correspond to 3 operators in gravitationally addressed Ising model: the unity operator, the spin operator, and the energy operator. And the residue formulas here, they give such relations. So you see that T, these flat times, are expressed as polynomials of the coefficients of these two Krichever polynomials. And in this, these expressions are very simple, but these are algebraic relations for the coefficients themselves, and they cannot be always solved back. But sometimes there are some, say, simplification. If you solve this, this equation can be solved for x naught, and rewriting then the first one, you get it in the form of so-called Bulatov-Kazakov equation, which was discovered by Dima Bulatov and Volodya Kazakov in the context of gravitational addressed Ising model, well, yet in 80s. So, well, another possible example what this theory gives is for the PQ equal to 2, 2k plus 1 series. It's the next simplest after this p comma 1 case, and here things can be still simplified and you can get something. So first of all, well, there are, since p equal 2, corresponds to the mostly well-known reduction of Kp, and here dispersion is Kp, the KdV equation. So it's just the x is second order polynomial, comes from second order differential operator for Kp, which we saw in the previous talk. So here everything is very simple. So there is only one equation at dx equals to 0, which gives you this polynomial equation for the so-called string equation, dispersionist string equation in the two-dimensional gravity of this series. And well, here it can be even something can be integrated up to something. And for example, an explicit formula for the quasi-classical tau function exists. So this what comes from Krichever theory, and here it can be computed more or less explicitly in terms of this u variable, and u obeys this algebraic equation, and this is coincides to another equation used long ago in the context of matrix models. Which? Kinetic energy of what? In Pasha's case? No, well, I'm sorry. Here u is u because u is in KdV, yeah? And he had q in KdV. You mean this, yeah? To be honest, I don't see any analogy with kinetic energy, but well, I see. You mean that is just moment. Great, yeah. Yeah, just for the course of Hamiltonian mechanics. Okay, but well, there are problems, and one of the problems, the main problems with comparison to Welchit theory is that there are so-called resonances, that there are possible nonlinear transformations in the space of couplings, and these flat times of Krichever theory do not necessarily correspond to the common choice of couplings in Welchit theory. And these nonlinear transformations are not really well understood in the context of Kp, but in this particular case, you can use the fact that you can exchange P and Q, vice versa, and in the big reduction to K plus 1 reduction, these resonances are absent. And I will now try to exploit this fact and give some consequence which coming here from this residue formula. This is, I will omit, but it includes this non-trivial issue of this PQ duality. And the puzzle which actually I found with a big help from Sasha Artemiev, who is here, and Pasha Gavrilenko, my former PhD student, is that what here comes out, the Krichever formula gives rise to very well known and not well understood by myself, Verlinde formula from two-dimensional conformal theory. In order to do this, we have to come to the Welchit background. So to consider the case where only cosmological constant is not equal to 0. This is already in Kp a non-trivial thing, because in different models, this mu corresponds to different Kp time. And this is, well, I will refer to maybe following the great Seiberg, by Chebyshev background, because it's here the curve can be written in terms of Chebyshev polynomials. Now, what are these Chebyshev curves? The statement is that if only you restrict to the case when only this cosmological times is not equal to 0, then this polynomial equation for the curve acquires the form of equality between two Chebyshev polynomials of the second kind of these mutually dual powers, P and Q. And of course, this is a rational curve. This is polynomial. It can be parameterized by coordinate on two-dimensional sphere or on CP1. And due to the very nice property of these polynomials, it can be parameterized again by dual formulas. So if such equation holds, then X is a Chebyshev polynomial of power P, and Y is a Chebyshev polynomial of power Q. So this curve is degenerate at the points where the derivatives of this and the nice theory of Chebyshev polynomial says that if you take a derivative of one sort, you get another sort. So it degenerates at these points, and actually for this series, it's a degenerate hyperelliptic curve with nodal singularities. So at y equals to 0 and all zeros of this equation. Well, there is some clever advanced brain interpretation of that, which I will not touch because I do not really understand it myself. But in practice, it looks like that this is just a rational curve. And in terms of these coordinates x and y, there is just two k pairwise glued points where the singularity appears. And formulas here are very simple due to relation between these polynomials and trigonometric functions. So that's basically the picture. So we have this curve for this minimal series. So as I said, it's degenerate. And important point are the following. So these are the points of nodal singularities, which were denoted by like Z10 plus minus. There is one point z equals to 0 where dx vanishes. And there are more points where dy vanishes. You always can easily see it from this picture. And these are the important points because the rest of the formula will be somehow located on them. Well, maybe let me even skip all this set of this Chebyshev algebra and ground rings and whatever, and come directly to the residue formula. So let's consider it on this curve, where by some convenience of notation, I will sometimes use tilde indices. It's not a big deal just because in this 2k plus 1 for high k, this corresponds to coupling of non-unitary conformal field theory with the fields of negative dimensions with minimal gravity. And that's why the cosmological constant corresponds to some higher kp time, which corresponds to the operator of Wiltshire dimension 0. But we can now simply skip these details, just consider this formula, which should be localized at dy equals to 0. So it means that it localized to the set of zeros of this equation, where this u to k is corresponding Chebyshev polynomial. And those zeros, as I said, were denoted so in this, on this picture. They can be easily found, some points zeta plus minus. And if you just make this simple computation and use the relation, so first find the zeros in terms of these cosines, find the values of x's, find the value of y's there. This just simply gives rise to certain sign factor. And the only non-trivial relation is that, which you have to compute the second derivative. You just plug it into this formula and finally get at the end such expression. This sum with three sine functions in the numerator and one sine function in the denominator. So, well, first of all, of course, you can think that this sum of sines can be just found in some Grotstein-Rezek, but that's not true. And that's not true because actually it corresponds to the Verlinde formula for this particular conformal theory. And the result is given up to certain normalization, which I probably chosen in a stupid way, but it corresponds to this NIGK, where are the coefficients of the fusion algebras, And in this case, they're all either unities or zeros. So just this brief reminder of this Verlinde formula. It's a very actually non-trivial statement, and I don't know any simple proof of it. Yeah, there are some. What is trivial? You see? What do you mean pretty much by definition? Yeah, but what do you mean by definition? Again, we can maybe discuss later, but for me it's very non-trivial. So why? Why? Because what is S here? S is a matrix of. I didn't get. I didn't get. What is Fourier transform? Yeah, but the Verlinde formula relates the matrix of modular transformation of toric blocks with the coefficients of fusion algebra. Right now I don't want. I want you to explain me later, but not right now. Yeah. I think formula for dimension is much more trivial than that one. Yeah, I think so. But this one is very non-trivial, just even ideologically. Maybe you can tell me, because, well, it gives you relation between the quantities which are defined locally, just from fusion algebra, and some global transformation on Tor. Yes. Well, but I'm starting with CFT. In TFT, but it's different, then I have to prove that it's the same. I see. Okay, but anyhow, for me, again, it's a non-trivial statement, which cannot be checked directly. And the problem is that, yeah, it's relate this S matrix of modular transformation, which is actually, in the case of minimal model, squares to unity, with this coefficient of fusion algebra. The formulas for minimal models are well known. You can find them, say, in well, any good book on conformal theory given by this expression. And in this particular case, one of these indices is necessarily equals to 1 because of this 2 reduction. And then you just get this expression, and you see that basically which we had on a previous page. So what I found myself, well, at least maybe trivial for everyone, but it's very non-trivial for myself, that now this formula holds here. Indeed, it coincides totally with the physical intuition. Once you started with this minimal gravity, in this definition, you sort of ensure the minimality. Of course, you have something related with this fusion algebra for the 3-point functions. That is obvious. But what I would say, not very obvious, and what is nice here, that actually Krichever's formula gives a proof here of Verlinde formula. And proof, well, you will see, maybe it technically causes some questions, but ideologically it's very simple. You have here the sum of signs, and it arises from the sum of the zeros of one of the differentials. But you can move the contour. And then the contour moves to the zero of other differential, which is a single point that equals to 0, and some here non-trivial contribution from infinity. And once you write it in such a way, then these residues can be just computed. You can, one of the residues is computed immediately, and another one is computed after some simple manipulation, and you end up with this expression. And indeed, you can check that so define this Nijk for any set of indices are either zeros or ones. So here, well, kind of a puzzle was that from this Krichever formula, you find this Verlinde formula. And one maybe remark at the end is that on some, maybe last month, fancy conferences, there were some talks which were actually giving the infinite generalization of this formula, this set of sum, now infinite sum over the sine functions. And this is for the case of non-minimal gravity and for the case which Igor didn't like of non-algebraic curves. So here, but basically it's just the same as was written before. You forget about Chebyshev polynomials and consider this cosine expression, parameterizing these x and y variables. And then when you apply residue formula, you just get this expression. What stays in the numerator, as I explained, was literally corresponding with the zero value in the coefficient, etc., etc. And this formula is believed to be equal to the Zamolodchikov's formula for the 3-point function in non-minimal theory, where the matter is which couples to Liouville gravity is also given by a kind of Liouville type conformal field theory. But as I said, if you just apply here this formula, you get again this expression, and you can simply compute what stays in the denominator and get the right result under again a simple assumption that these phi's are given by the same sine function like it would be in the case of minimal theory. And this is the plot of this non-algebraic curve if you want to have a look. The sum over the x is infinite. I'm just saying that Krichever formula, if you substitute there this formal data, gives non-algebraic, gives just this expression, which was announced by these clever people from some sources which I cannot even pronounce, something like GT or whatever. Okay, maybe you'll tell me because I don't know. Okay, so that's kind of a puzzle, and there are, well, many topics which actually deserve some discussion and which develop these original ideas of Igor Krichever. So, and I tried just to list them briefly, those known to me. So the story started with instanton partition functions, which were defined and calculated by Nekrasov, and which in the certain limit give back the quasi-classical tau functions. They tend to be related with two-dimensional conformal field theories. It's again a story, and which this story is actually especially important if you consider so-called relativistic or certain QG deformations. Again, having some clear meaning from the physical point of view. And that all, there is another set of issues related with topological vertices, cluster algebras, double loop algebras, whatever. And finally, with these tau functions of isomonodromic deformations. And actually, it looks like now that this Krichever tau function is just the first term in the expansion of the tau functions obtained in the context of isomonodromic problems. So there are very many interesting topics yet to be developed, but, well, fortunately or unfortunately, we don't have time for their discussion. So, thanks for attention. And if you have any questions.
Comments?
Yeah, boy.
Well, I have a question about the connection with PQ minimal models. When you define the polynomials x and y and some curve by the equation, and how to understand that it's connected to minimal model.
Wow. To compare the correlators, the result of computation of the correlators in the Welchit theory and in the theory. Well, first of all, in these old days, there was a nice simple formula developed for the so-called string susceptibility. So how the partition function scales with respect to cosmological constant. That's a simple issue. But sometimes it's not enough, and it gave rise to certain mistakes. But in order to be sure, you have to, in principle, to compare all possible correlators. That's a non-simple task, but there is a progress. But somehow, what is not possible, I think, and which is at least very hard to do, is to derive this formulation from worldsheet theory directly. It was kind of, you know, of coincidence, clear intuitively on physical ground, but not proven mathematically. Correlators computed in KP with the correlators computed in worldsheet theory. You should be very careful. You should consider only the ratios which do not depend on the particular redefinitions of times. So it's a big work. But in principle, sometimes you can do this.
Any other questions?
Well, but in such general terms, everything is connected. Yeah.
Anybody else? Okay, then let's thank the speaker again. And we are making the lunch break.